Hello everyone and welcome to our group presentation weekly project update, and for this week we are covering multi-threading, virtual memory and address translation. So our group members, I am Nelson Muchonji, we have Elio Waga, Jean Litema, Jacinta Rico and Kevin Ogechi. So for the first part, I'll invite Jean to take us through.
Okay, thank you, Nelson. So I'm going to give you reasons why a multi-threaded solution is better than a single-threaded solution. So first of all, a kernel thread can request for data which is not currently on the main memory. So what happens after this is that the data is going to be looked for in the virtual memory, and as a result, there's going to be a page fault. So in a multi-threaded solution, another kernel can be switched to use the interleaving time in a useful manner. A single-threaded solution is not capable of this, and thus, multi-threaded solution is better where a program encounters several page faults or interrupt, e.g., waiting for another system. So this is better because it has multiple threads. Another one can come in place of the other when a page fault occurs. So in a single-threaded solution, when a page fault occurs, that will be like the end of it. But in a multi-threaded solution, one will be able to pick up for another. Let's kindly continue.
Okay. Thank you, Jean, for that. So I'll take you through virtual memory. And virtual memory is a feature of an operating system which basically lets the computer to compensate for shortages of physical memory by transferring data from RAM to a disk storage. So for that, to bring back the pages, because at first you have to move the given data from the physical memory to the virtual memory, and there are times that you will need to bring back the previous pages that you moved. So the operating system, what it does, it moves the other pages to a hard disk in order to create space through a process called paging, or also called swapping. And so the space on the hard disk, which we can call it a page file or a swap file. And what it does, that the computer's memory manager, it carries the swapping happening so quickly through algorithms which they include the least recently used, famously known as LRU, least frequently used, known as LFU, or most recently used. So there are different ways that you can realize virtual memory, which include paging. And for paging, it involves physical memory, which is partitioned into equal size page frames, in that each page frame can avoid external fragmentation. And the memory frame consists of a pair of FO, whereby we have FO is the frame and O is the frame offset. So I'll invite Kevin Ogechi, who will further explain about the same. Ogechi, welcome.
Okay, so this is an example of a translation of virtual address to a physical address. So the drawing currently on the slide, you can the 0 times 000 is the disk, and we have the 0 times 001 and 2 and 3. So these are the virtual page numbers, and they are mapped to their responding numbers in the physical page number. So in this case, we are using an example of a virtual page number of 0003, which is mapped to a physical page number of 006. So as Muchonji explained, we are using a virtual address. We are using a virtual memory to allow programmers to use a small amount of memory efficiently and effectively. So in this case, you have a 32-bit virtual memory and 28-bit physical memory. So the page offset are the same, 0 times 0 times 204, and on the right side of the slide it shows the virtual number and the page offset. So that's what I had. Maybe Mchwanji, if you could add something on that.
Thank you, Kevin. Just as I had mentioned earlier on, is that when we have data that exceeds the given memory, so the that data will be converted into pages and then it will be moved into the virtual memory. So later on we might need to have that given data, and so the virtual memory, it has to send back the given message into the physical memory. In order to do that, we used an example of a translation whereby we had a 28-bit, and of which of those 28-bit of physical memory and then 32 bits of virtual memory. So out of that, we had 12 bits which are offset, and as you can see from the given diagram, the translation of the 12 bits is 0.204, and which directly translates into the physical page number, of which it is the same page offset. And then basing on the remaining, which is 20 bits, when translated it comes into 0.003, and using the page table which converts, and as we have 0.003 basing on our page table, which is going to help us in mapping the given virtual page number into the physical page number. So it gives us for 0.003, which translates to 0.006 for the physical memory. And so basically that's how it functions. So I want to thank everyone for your time, and in case you have any questions, feel free to forward them to us and we shall respond to them. So thank you till we meet next time during our next presentation.